Hi, I'm Sarah. I am a community college student currently in Chem 1B, and today I will be teaching you section 18.8 on complex ion equilibria. So, did you know that complex ion equilibria can help us understand why certain chemicals are used in devices like conventional black and white photography? According to chem.libretext.com, black and white photographic film contains light-sensitive microcrystals of silver bromide, or mixtures of silver bromide and other silver halides. Silver bromide is a sparingly soluble salt, and that's a salt with very low solubility, with a KSP of 5.35 times 10 to the negative 13th at room temperature, 25 degrees Celsius. So, when the shutter of the camera opens, the light from the object being photographed strikes some of the crystals on the film and initiates a photochemical reaction that converts silver bromide to black silver metal. Well-formed, stable negative images appear in tones of gray, corresponding to the number of grains of silver bromide converted, with the areas exposed to the most light being darkest. You've probably seen this in Polaroids, maybe. To fix the image and prevent more silver bromide crystals from being converted to silver metal during processing of the film, the unreacted silver bromide on the film is removed using a complexation reaction to dissolve the sparingly soluble salt. So the equilibrium tends to the left, and the equilibrium concentrations of silver plus ion and bromide minus ions are very low, in the 10 to the negative 7th. As a result, removing unreacted silver bromide from even a single roll of film using pure water would require tens of thousands of liters of water and a great deal of time. Le Chatelier's principle tells us, however, that we can drive the reaction to the right, so the other way, by removing one of the products, which will cause more silver bromide to dissolve. In photographic processing, excess silver bromide is dissolved using a concentrated solution of sodium thiosulfate. Comparing K with KSP shows that the formation of the complex ion increases the solubility of silver bromide by approximately 3 times 10 to the 13th. The dramatic increase in solubility combined with the low cost and low toxicity explains why sodium thiosulfate is almost universally used for developing black and white film. Moving on to the info that the average Chem 1B student should already know, we will start off with the law of mass action. So, this law states that the rate of any chemical reaction is equal to the product of the masses of the reactants to their stoichiometric coefficients. Bringing K into this, recall that K is our equilibrium constant and the particular ratio of products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients at equilibrium equals a constant, which is K in this example. Going to my second bullet point, we have Le Chatelier's principle. This one is quite simple. Le Chatelier found that when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. Basically, a system at equilibrium tends to maintain that equilibrium. It bounces back when it's disturbed. Onto the ice tables. Ice tables usually consist of a chemical reaction and a 3-row table below that reaction. Ice stands for the 3 rows: initial, change, and equilibrium. Recall that solids, pure liquids, catalysts, and noble gases do not affect equilibrium. When solving for an unknown value in an ice table, instead of using a quadratic, sometimes an assumption or approximation can be made. An assumption simplifies the calculations without any significant loss of accuracy. There is only one guaranteed way to know if you may use an assumption, though. That guaranteed way is the check. After using the assumption and finding your unknown value, plug the initial value over the value you just found and multiply it by 100. If it is less than or equal to 5%, you are good to go. Lastly, remember that Ksp is the solubility product constant and that it represents the dissolution of ionic compounds. Perfect. Important new info to learn for this section is that the Kf is the formation constant, and it equals, similar to K, the concentration of products raised to their stoichiometric coefficients over the concentration of reactants raised to their stoichiometric coefficients. Next, we have 3 different figures found in the textbook. Please feel free to pause when I go over them if you'd like to take a longer look to better understand them. I've highlighted the page numbers so you can find them on your own as well. First, there is the complex ion formation figure, illustrating how insoluble silver chloride usually is made soluble by the addition of ammonia, which then forms a complex ion with the silver ion and dissolves the silver chloride. Second, we have the amphoteric hydroxide figure, clearly showing us how varying pH levels affect the solubility of amphoteric hydroxide. And third, we have the Kf of specific complex ions in H2O at 25 degrees Celsius, usually room temperature. It's important to know that you can utilize this table filled with formation constant values of common complex ions when applicable in later problems. All right, let's discuss. These are some questions you should be asking yourself, and hopefully with repetition you will be able to confidently answer without any notes. 1. What is a complex ion? So a complex ion is an ion that has a central metal ion coordinated, which means covalent bond, to 2 or more ligands, which are neutral molecules or ions that act as Lewis bases with the central metal ion. A Lewis base is an electron pair donor with hopes to one day find the perfect electron pair acceptor, Lewis acid, and eventually settle down together to form a Lewis adduct. 2. What is the equilibrium constant for the formation of complex ions? So Kf, the formation constant, equals concentration of products to their stoichiometric coefficients over the concentration of reactants raised to their stoichiometric coefficients. 3. What is the effect of complex ion equilibria on solubility? The solubility of an ionic compound containing a metal cation that forms complex ions increases in the presence of Lewis bases that complex form with the cation. This is because the formation of the complex ion drives the dissolution reaction to the right. It increases the concentration of reactants. 4. How do amphoteric metal hydroxides solubility differ from non-amphoteric metal hydroxide solubility? All metal hydroxides become more soluble in acids, but amphoteric metal hydroxides also become more soluble in bases. So go ahead and pause real quick to read the question for yourself, but I'm going to get started by writing out the balanced equation for the complex ion equilibrium. I looked up the Kf value in the table, and now I'm solving for the initial concentrations of copper and ammonias next. After I find the initial concentrations, I just want to put in a reminder that molarity is moles over liters, and that before writing out your ICE table, you should always write out the equilibrium equation. And in this case, that is the concentration of tetraamine copper 2 ion over the concentration of the copper 2 ion times the concentration of ammonia quadrupled. So now we're moving on to the ICE table. Go ahead and take that balanced equation, put it right above it, and add in the values you're given. In this case, that's our initial values. Now, already thinking ahead, we know that the Kf is pretty large. It's e to the 13th, that's 10 to the 13th. It's a lot of zeros, so we are going to assume and hopefully save some time. The assumption here represents that the reaction will be driven to the right so that most of the copper 2 ion is consumed. Now all we've got to do is substitute the expressions for the equilibrium concentrations into the expression for the formation constant, which we did above, which helped out, and solve for x. Taking it step by step, what I do first is multiply the denominator, which includes x, to both sides to get rid of it. Then I divide both sides, by the number in front of x to isolate x, and we get our answer. But remember, we use the assumption. So what do we have to do? We have to check it, and to do that, you put it over the initial, multiply by 100, and since it's less than or equal to 5, we are good. The remaining concentration is 2.7, E negative 13. So this is a you try problem. Go ahead and pause the video and try it on your own. Due to time constraints, I'm just going to quickly go over the answer to this problem. So first I wrote out the balanced equation, then you should have found the Kf in the table, and then first written out your equilibrium equation. You want to write the balanced equation up top over the ice table. Then, again, you should have realized, hey, this Kf is pretty large. Let's try to assume and omit the x's. So we did that. Then we plugged it all in to our Kf that we figured out above. We solved for x, giving us 8.7, E negative 10. However, you
must check.
So we put it over the initial, multiplied by 100. We were good to go. The answer should be B.